Hello and welcome to this video on interest risk and duration analysis. For this video I planned the following. First of all, I would like to define what risk is, and then I would like to go into duration analysis, explicitly into dollar and euro duration, the Macaulay duration, and the modified duration. And last but not least, I would like to introduce the present value of a basis point. Okay, so what is risk? A risk is nowadays defined as a deviation of the actual result from the expected result, what we call the deviation risk. So here we see some kind of risk distribution or probability distribution. And in the middle we have the expected value, and a deviation, whether it is negative or positive, is understood as a deviation risk. So, since from the point of view of the person or company affected, the deviation in earnings can be both positive or negative. Risks can be measured, for example, with the help of variance or standard deviation. In another view, risk is understood only as a possible negative deviation, what we call the downside risk. So we only see the negative part of this. Generally speaking, the risk can be differentiated into the probability, which is denoted by the area under the curve, and the severity, so the amount or the severity of this downside risk, so how far we go downside. Both, of course, can be managed separately. So we can manage the probability and we can manage the severity. Let us come to duration analysis. So, from an economic point of view, risk can be understood as a change of the present value. So, to understand how much the present value of an investment changes, if, in this case, the interest rate changes, we can simply derive the present value formula with respect to the interest rate. We will obtain the euro duration then. So here we see a simple present value formula to value any kind of investment, for example a bond. But all other investments will do more or less the same. If we now derive with respect to the interest rate, we are going to write it del PV, del present value, with respect to del R, because we derive with respect to the interest rate. Since here's no interest rate, and this is a simple sum formula, we just need to derive the last part here. And if we do so, of course, we're going to subtract 1 from the exponent here, which will lead to minus t plus 1, and the minus will end up in front and the t will end up here. If we go a little step further, we can take out the 1 here and rewrite the whole formula as del PV, del present value, with respect to del R equals minus 1 divided by 1 plus R. So this comes from taking out the exponent here, the sum of all cash flows times, and this is the important point, times the point of time where the cash flows occur, times the discount factor. So this formula is called the dollar duration or in Europe, the euro duration. So we see a change in the interest rate leads to a change in the euro value of a bond or of any other investment. Of course, we need here a combination of the chain rule and the power rule, and accordingly, we have the t isolated here. Accordingly, the duration is measured in years. A rough approximation of the change in the present value can be derived as follows. So the change of the present value equals the euro duration times the change of the interest rate. But we have a convexity problem in this function, and this is only a linear approximation. So the smaller the change in the interest rate is, the better is this formula. The larger it is, the worse it becomes. A better approximation can be achieved using the Taylor series development, where convexity and further derivations can be taken into account. If we now take this formula and divide by present value, we get the percentual change of the present value due to a change in the interest rate. So here is divided by present value, and here this term divides by present value too. The inner term of this formula, skipping this part, only this part here, the inner term of this formula is called Macaulay duration, dMac. Due to the Macaulay duration, the percentual change of the present value equals the present value weighted capital binding period. So here we have a discount factor, that's why it is present value weighted. And here we have the capital times the binding period. So we have cash flow and discount factor is present value times t, present value weighted capital binding period. However, it is immediately noticeable that Macaulay has omitted this specific term here, so that the Macaulay duration will not give completely correct results. If you add the omitted term, you get the modified duration, d mod, so we have the term in here. Now, some conclusions can be made on the duration concept. Considering zero bonds, the duration perfectly equals the maturity. Accordingly, a zero coupon bond has a much greater interest sensitivity than a coupon bond with the same maturity, where coupon payments are made annually or quarterly. Considering a coupon bond, the lower the coupon, the higher the duration. In the extreme case of a zero coupon bond, the duration corresponds to the remaining term of the bond. In addition to the maturity of a bond, the timing of the payments is also important. The duration links these two relevant components in a multiplicative way, i.e., it weighs the respective payment date t with a relative contribution to the present value. A higher duration indicates a tendency towards high interest rate sensitivity and shows how long the capital is captured on average. However, since interest rates usually change gradually, discretely, rather than continuously, and the bond price's dependence on the interest rate is not a linear relationship, the changes that the duration calculates are not entirely exact. The fall in price is overestimated when the interest rate rises, and the rise in price is underestimated when the interest rate falls. This error is triggered by the approximation of a nonlinear relationship by a linear one. Is of little significance with only small interest rate changes. However, with large interest rate changes, this convexity error rises sharply. The inclusion of convexity in price estimation offers a mitigating effect on this error. A very large disadvantage, however, results from the assumption of a flat interest rate structure. Because in the aforementioned net present value formula, the interest rate was discounted at a uniform interest rate R and not at a maturity adjusted interest rate RT. To take this into account, we come to the present value of a basis point. The present value of a basis point, PVBP, sometimes also called price value of a basis point, is an absolute sensitivity indicator for interest rate instruments or portfolios, consisting of them to analyze the interest rate induced price risk. This indicator is also often referred to as basis point value, BPV, or dollar value of a 01, DV01. For fixed income securities, for example, the PVBP, present value of a basis point, indicates how much the dirty price of a security changes if the yield curve shifts by 1 basis point, i.e. by 0.01 percentage points. The calculation is possible using the present value approach. Assuming again a flat yield curve, the present value of a basis point is related to the concept of the modified duration. The present value of a basis point then is the modified duration times the present value divided by 10,000. The present value of a basis point is used, for example, in the risk management of banks and insurance companies. However, the present value of a basis point is also inadequate, as a uniform shift of the yield curve is rather unlikely. Ultimately, it is known that the yield curve reacts much more slowly and weaker at the long end than at the short end. A tilting of the yield curve is therefore much more likely than a shift. For this reason, banks and insurers today use realistic scenarios in their interest rate risk management. Some of these scenarios are based on so-called stress scenarios, which are intended to represent the change in the yield curve in an extreme economic environment. Thank you for listening to this video. See you in the next video.